Okay, good afternoon, everybody. It is 12 o'clock on the dot here in New Orleans, Louisiana. We are Central Time, but anyway, so glad to welcome everybody today for our webinar about what you've been seeing going, on your screen. Trinity, the first test of the atomic bomb, and then also using the atomic bombs in World War II. That's really our focus today, and we will be joined by an awesome graphic novelist. His name is Jonathan Fetter-Vorm during the second half of this presentation today, and he's going to be sharing with you a bit from his graphic novel Trinity. He'll actually be reading a portion of it for you as well and answering any questions you guys have. Before we get started, I just want to give you a few reminders about how this program actually works. So first off, to say that Adobe Connect, which is the software that we're using right now, eats up a lot of bandwidth. So if you could, it'll make your experience a little bit better, and hopefully everything will stream a little faster. Close out any programs that are using the internet right now. That'll kind of help that situation. If you have any stalling or lagging or anything like that, something funny, I always say, X out of here and refresh your window. Sometimes I don't know why that does the trick, but it does. So, and then lastly, hopefully we're coming through clear enough here. But sometimes the volume levels differ between the videos we play and, the live microphone. So what I would love for you all to do, if you could, is you can adjust your speaker volume throughout the program, either manually on your computer, or you see there's a top menu bar at the top of this window here, and you'll see a speaker icon next to on that menu bar. If you click that little arrow next to it, it'll allow you to adjust your speaker or your microphone volume, or speaker volume, in here. So that'll allow you to adjust if there's any kind of changes in volume, which sometimes happen with this platform. Also to know too, we're going to move from this area in here, and then we're going to transition into another webinar room in just 1 second. So actually, let's do that right now. So you're going to see your screen change, and also you're going to see me hopefully in 1 second. And let's adjust this here before we put the camera on. There we go. Now let me adjust this some more. You can't even see us. That helps. Okay, awesome. So I'm going to start sharing, and you all can see me, Chrissy. Hey everyone. I'm the virtual classroom coordinator here at the museum. This is Rob Wallace. He's our STEM education coordinator. And today we'll be talking about this very subject you see on screen. What we'll have you do for the rest of the program, you've seen that chat pod went away. Below us now is something called a Q&A pod. And if you have questions for us, and then eventually questions for Jonathan, the graphic novelist, please type them in that Q&A pod there. We'll be looking at them throughout the program, seeing if there's any good questions popping up. Also, teachers in the room, I just wanted to let you know before we kind of get started here and forget, this session is being recorded right now, especially for that Distance Learning Academy where lots of students are watching from Michigan. So you'll be able to access this anytime after the program's over, and I will be sending everyone an email after on how to actually access this. So today we're gonna, really dive into how this invention, atomic bomb, how it was created in really such a short span of time. As you're going to see, we're going to go through a timeline today, and you'll see that. We'll be examining the discoveries of scientists to create, one of the most powerful weapons the world has ever seen. You'll notice that Rob and I, and eventually Jonathan, we're going to be talking about these same events in kind of in different ways. Sometimes you can tell the same story in multiple ways. You're going to see that today. We're going to obviously be live on camera here and doing some demonstrations and showing you some slides. And Jonathan's going to read a portion of his graphic novel to you all in just a bit. So some of the same sort of concepts delivered in very different ways, which I think will be a lot of fun today. And so that's how we're going to really explore this, especially examining the science behind it, at least as best as we can in an hour. So that's our goal here, to be done by 1 o'clock. So even though we could probably talk about this topic for at least a few weeks, if not, so we don't want to keep you that long. So let's dive right in, actually, with I always like to start these programs with a poll question, And I know actually this poll might block what this is, but you guys should hopefully know this off the top of the bat. So we're gonna, let's see here, I got that poll up. So what is this on screen? Maybe I can put it, let me actually move this and put it above it so you guys can really see. What do you think this is? And I'm gonna broadcast the results in just a second here. All right, this has maybe been an easy question. I'll give it a few more minutes or a few more seconds. All right, I think I asked too easy of a question. Hopefully we'll challenge you guys later.
It's an iconic image.
Yes. So, broadcasting, yes, you all know that this is an atom. We can't start this program without talking about, an atom, and because we're going to be starting with this very small and then working large, right? So, very good, everybody. Yes, this is an atom. All right, hopefully I can test your knowledge later, too. So, we know the different parts of an atom. We're going to point out the electrons here. And then, of course, we'll be talking about this protons and neutrons we'll be talking about a lot today, forming the nucleus. And you all know that we're made of atoms. We're surrounded by billions of atoms. And when we talk about the atomic bomb eventually, we're not just going to be talking about one atom. We're talking about billions and billions of atoms doing this reaction that we're about to show you here on screen. And we're going to start off, we're going to do this kind of as a timeline chronologically here. And we're going to start off with 1939 with the discovery, of fission. Scientists, they were running these different kinds of experiments to learn about atoms and their properties and all of their potential. And during these experiments, the scientists got some strange results. And in one of these tests, they were going through these different processes with uranium atoms, and they saw that the nucleus of these atoms split, and they weren't really sure of what to make of the results.
Yeah, they had a sample of uranium, and they were shooting neutrons at it to try to see what would happen. And really, they were trying to understand, how is a nucleus of an atom built? What is it like? And so they were shooting neutrons at it. They had recently figured out how to do that, and it was actually in 1938. And a reaction occurred. They found out that they had some other chemicals in there, and that it wasn't uranium anymore. And they got a ton of energy released at the same time, and they weren't sure what to do about it. These were two guys in Germany doing this research. It's interesting that most of the research on fission and atoms and stuff was being done in Germany. And a collaborator of theirs, Lisa Meitner, had to move to Sweden because she was a Jewish person, and so she had to leave Germany and go to, and they wrote her, sent her the results, and she said, oh, what's happened is that uranium has split in half, and that's why you don't have uranium anymore. You have these two other chemicals, and she named it fission.
So fission, kind of a basic definition, it's a reaction where the nucleus of an atom, it's split, and all of that energy is released, and it is a tremendous amount of energy. And actually, to demonstrate that, we have a little video for you today. We've got a couple videos. They're a little bit silly, I'm going to tell you right now. In this video, we're going to actually use a balloon to mimic what a nucleus would be like. And we're going to split that nucleus and see what happens. We're going to do it in slow motion too, so watch out. So what I'm going to do for all of these clips, everyone, just so you know, to make sure that they play nicely, crossing my fingers here, I'm going to pause our camera here live, play that.
So I'm Rob, and I'm here to explain Niels Bohr's droplet model of the nucleus and fission. So a nucleus is like a big liquid drop, he said. And when the nucleus gets big and unstable, it can split. And so energy can come in, and it can force the two sides apart, and then something can come in, like a neutron, and it can split the two sides. And they have a lot of energy when they split. Let's see it again in slow motion.
I feel like I should have slowed that down even more for you all, because even in that very slow motion, you saw how quickly those two sides of the balloon, went the other way, right? Went the opposite ways from each other. That's the kind, as I said, mimicking this kind of energy when you split a nucleus. So when we were talking about actually German scientists working on this, kind of relates to what's going on here in our next slide. So they were worried about, as they were studying this energy, potential, they were starting to figure that through this process called fission, they thought that maybe this release of energy and release of lots of energy, that could be potentially used to create a weapon. And so many of these scientists making these deductions, as I said, were from Europe and specifically Germany. And they had a fear that with war breaking out, look at the year, it's 1939, these discoveries could be put into use by, the wrong people. So actually 2 scientists approached Albert Einstein, who you see here, and they asked Einstein to write a letter to President Roosevelt about the potential of this energy and how it could be used. As I said, think about it, Nazi Germany, they had the potential maybe of developing this sort of weapon. And with Hitler seizing territory throughout Europe, this became really scary, right? So this is the letter that Einstein wrote to the president.
Right, and the 2 scientists, I think one of them was Polish and one of them was Czech. And so they came to Einstein because Einstein was a very famous, very respected scientist, and they knew that he would share their concerns. And actually, Niels Bohr had brought the news of, right before war broke out in 1939, Niels Bohr had come to a conference in Washington, D.C. and talked about the results of fission. And Marshall, you asked about fission and why do we call it fission? And she just borrowed a term from biology. The other time in science when we talk about fission is when single-celled organisms like bacteria, when they split, they call that fission. So it's the same sort of thing. It's a word that means splitting or into 2.
Great. Thanks for answering that question. So with this news and with this letter that Roosevelt receives, he decides to create an advisory committee on uranium. But really, it's kind of slow moving between 1940 and 41,
what government
right?
advisory committees do. They don't go very fast.
Yeah, well, if anything, they decided to rename it the Advisory Committee on Uranium. First, it was like the S1 project, and then it became the Manhattan Project. If you have uranium in your title, right, it's not secretive
enough. That's not very secret what you're doing.
Yeah, exactly. But that changed with a big event, and here's where I get to ask you another poll question. And that big event was this. It happened on December 7th of 1941. Or another way to ask you this is, well, how did the United States get involved in World War II? Thinking this might be another easy question, but I'm going to put it out there. And, oh yeah, man, I should have challenged you all more. I'm going to let it kind of go, and then I'll reveal the results. But everybody's looks like they're on their A game today. So, all right, I'm going to broadcast, yes. The United States got involved in World War II because Japan attacked Pearl Harbor, Hawaii. It was a surprise attack, a secret attack. As we saw, I'm going to hide this poll, on December 7th of 1941, and our U.S. Pacific Fleet that was stationed at Pearl Harbor, Hawaii was attacked. 2,400 plus Americans died in the attack. And then on December 8th, as we see here,
yesterday, December 7th, 1941, a date which will live in infamy. The United States of America was suddenly and deliberately attacked by naval and air forces of the Empire of Japan.
So in that famous speech, as I said, Roosevelt is asking Congress to declare war on Japan. That happens almost unanimously. And then a few days after that, Germany declares war on the U.S. So if we think about it, within the span of, less than a week, the United States is attacked, the U.S. declares war, and then someone else or other countries declare war on the United States. So that kind of speeds up then this process. It's
kind of funny that
Manhattan
an attack by Japan caused us to move forward our concern about Germany.
Yeah. But then in the end, the weapon was used. We'll get to that. We'll get to that. So by 1942, as I said, things start to speed up, and the War Department takes over the Manhattan Project. And under the leadership of Leslie Groves, who you see on screen there, there's a real picture, and then actually you can see just some of Jonathan's drawings too throughout this as well. So thanks, Jonathan, for that. And the scientific director, J. Robert Oppenheimer. The Manhattan Project would undertake this tremendous task of creating the atomic weapon. In total, these numbers astound me. The Manhattan Project employed 130,000 people, and it cost $2 billion. It was the largest scientific research project to date. And you can see, actually, look at all the places here on our map where the research and development took place all across the country.
There are others in Canada, too. And 3 of those places, Oak Ridge, Los Alamos, and the one in Washington State, those are still big government research centers.
Yeah. So, and we also see we're going to be talking about fuel development in 2 kind of key places in Oak Ridge, Tennessee, and then in Hanford, Washington. The other crazy thing, right, Rob, is that most people at these places didn't really realize what they were doing.
They had no idea what they were doing. They were just trained in a small, very specific thing, just do this, tell us when this needle goes over here.
Right. Yeah.
They didn't know what they were doing.
Giving specific tasks, and
that was most of them. All the scientists were concentrated at Los Alamos, so those guys did know what they were doing. Mm-hmm. Maybe not the clerical workers on site, but that's where they were building the bomb mechanism. Mm-hmm. So they really had to know what they were doing.
That's where actually J. Robert Oppenheimer set up shop in Los Alamos in New Mexico. And as I said, we'll talk about that a little bit more in just a bit. So we're going to go back to this whole idea of fission. And I just want to make sure that you all were paying attention here. And so I'm going to ask you one more time what fission is. So let's see what you guys say. Maybe this will be the most challenging of questions. And then I'll broadcast the results. Well, Rob, it looks like they might not have been listening. I don't know. Okay. Oh, now it's turning around.
Change your mind.
So you guys can flip-flop if you want. Change your mind here. You're also, if this does seem a little fuzzy material, as I said, Jonathan's going to be reading this his section about fission a little bit, so you can refresh your memory on that. Okay. All right, you do know what it is. So here you go. Yes, it is C, when the nucleus of an atom is split and energy is released. So we're going to go back to that idea. Instead of just talking about it with one atom, we need to talk about it with multiple atoms, mm-hmm. potentially hundreds of thousands and millions and billions of atoms, right? And that really was something that was discovered by this man, Enrico Fermi. He, in 1942, discovered what a sustained nuclear chain reaction was. Can you talk about that a little more, Rob?
Yeah, so first of all, this is like a huge moment in history. For thousands of years, people have been splitting compounds, splitting one compound from another compound, burning wood, making gunpowder. We've released energy by breaking atoms apart, one atom from another one. And then suddenly we've discovered how to split an atom itself, and that's way more energy. And what Fermi figured out was, we saw that fusion was undergoing, and he said, but is there a way to make it not just go poof, but to make it happen slowly and continuously and control the reaction? And it's kind of funny because he did this. They were supposed to be building a big lab for him out in the middle of nowhere, and they weren't going very fast. So there was a basement under the football field at the University of Chicago, and he built a nuclear reactor there, found a way to slow down the reaction so that it happened in a controlled way. And he got it to work. And then they immediately realized how dangerous this was, and they finished his lab out in the middle of nowhere so that he didn't blow up Chicago.
Well, a way to kind of demonstrate for you all today what a sustained nuclear chain reaction is, we're going to use, actually, let me hold it up so you can see. We're going to be showing you another video demo with Dominos. And as I said, Jonathan's going to show you how he illustrated the same sort of thing in just a little bit. This one also features. Hey everyone, Chrissy here, and what we're doing today is we're going to show you what a sustained nuclear chain reaction looks like. Now we can't use a microscope or anything like that to show you, so we need to blow it up a little bit. And so what we're going to do to represent atoms is actually using dominoes. So we are going to see how one nucleus of one atom splits and how it starts off a reaction. So let's test it out. You guys ready? Okay, so in this first row of dominoes here, this would be like a sustained nuclear chain reaction. But what is happening here is only with one atom splitting, causing another one to split. Something like this. In another type of sustained nuclear chain reaction, what we're trying to do instead, especially when creating a weapon, is we want that reaction to grow exponentially. So in this case, instead of one atom hitting another atom when it splits over and over and over again, we want one atom when it splits to hit two or more atoms. Kind of something like this domino setup. And imagine this going on and on and on and on and on. Okay, let's do it. Okay, let's slow it down and see that in slow motion. I love how those dominoes, for some reason, when they're slowed down to such a pace that they sound like bowling pins falling over. But think about that happening with billions and billions of atoms, as I said. That's the kind of reaction that we need to, eventually create a weapon. And that's kind of what they were looking for, too.
That's a lot of what they were calculating at Los Alamos was how much of these elements do we need to be able to put in one spot to make a big explosion like that.
Right. And
They
speaking
call
of
that critical mass.
critical mass. So there's a good vocabulary word for everybody. So speaking of elements, though, we are going to talk about the periodic table of elements, and actually a couple of them in particular. Now, Rob, isn't it right that, any element could potentially fission? You could split the nucleus of really any element, but there's some that are better than others,
Yep.
like uranium.
The bigger they are, when you packing, think about it. You guys know that a nucleus has lots of positive protons in it, and there's neutrons in it too. But eventually, you're packing all those positive charges in there, and the force that's holding them all together is not going to be able to hold them all together. So the bigger the nucleus, the more likely it is to split. And so if you look at the bottom of that periodic table, it's the ones way down at the bottom that are the ones that we think of as dangerous and nuclear and radioactive.
So so let's talk about actually uranium specifically. So uranium has, there it is right there. It has 92 protons inside its nucleus, and that's where you see the 92 in the corner here. And to get the atomic mass, which is that 238 in the bottom there, so there's that big nucleus. It would be taking 92 protons, and you add 146 neutrons, and that's how you get that 238 mass right there, where you see in the bottom of that element. And so that shows you it's a huge, huge nucleus. But there's some uranium in the world that exists that only actually has 143 neutrons.
Right.
So its mass is actually 235. And so the 235, why do you add 146, someone asked. 146 is also, that's the amount of neutrons in the nucleus. So the amount of protons plus the amount of neutrons together, boom, you get the 238 mass. So, but as I was saying, with the 235, that has only 143 neutrons, and that makes that nucleus even more unstable. And so it's so unstable, it's a lot easier to split, right? Yep. There's a lot less work, involved in splitting, those nuclei versus others.
And some isotopes are better than others for creating these reactions.
So you've maybe heard that term like enriched uranium before and maybe not known what it meant or what that entailed. Well, that's pulling out that isotope that's more unstable. An isotope is a variant of an element. What do you enrich uranium? What was that, a centrifuge, right? Something like that?
That's right. If you're following the news about Iran and watching their nuclear weapon development, there was talk about centrifuges and how many centrifuges were we going to let them have, and we sent them a virus that caused their centrifuges to blow up. And that's how you separate it out, because when things weigh a different amount, well, when you spin them around, the heavier ones are going to have more momentum and go to the outside. So just like you spin blood in a centrifuge to get all the blood cells down at the bottom of the plasma, it's the same thing. If you spin uranium, you're going to get the lighter 235, which is what you want, at the center and the heavier 238 on the outside. Now, 235, less than 1% of the uranium, if you just get uranium out of the ground, less than 1% of it is 235, and most of the rest is 238. And so it's hard work to get them apart.
Now, we have a demonstration for you all. Our centrifuge, well, we don't have a centrifuge here at the World War II Museum, but we have our own little version of it. It's a salad spinner. And what we're going to do is kind of show you how a centrifuge would work. I'm going to be moving the camera now, so you all, sorry if anybody gets seasick here, but this is, let me get the right angle here. Back it up. There we go.
All right, so this is 235.
That's the corn pops.
And these red beans, which are very important to us in New Orleans, are the 238. And you can see they're all mixed up, so I could slowly go through there. That would be a lot of work to get those 235s out. So what I can do is I can spin the centrifuge around. And now you can see that it's they're a little bit separated. So it takes a lot of work, but I can get some corn pops out of here. I mean 238 out of 235 out of here.
Yeah, corn pops.
And if I run it again, I can separate them even more. And so by doing this a few times, I can eventually get
all the corn pops, or most of them out.
Yeah.
Right.
And so it's a better way to get them out. It's a way to get them out and get what I want. Oops.
So, anybody want that concoction of corn pops and red beans? I don't know. That might not sound very appetizing.
They're kind of stale and sticky.
Yeah, stale corn pops and red beans. So, but anyway, that's U-235 and U-238. And so that is what they were doing. That's what they were working on in those two main places where they're doing bomb fuel production in Hanford, Washington. They're actually doing that same sort of thing, but with plutonium.
Well, what they're doing there is if you take 238 and you put it in a reactor for a long time, it becomes plutonium.
Okay, gotcha. So it's a little bit different, the process. But back in Oak Ridge, Tennessee, they're making uranium fuel. Now, so these places are working on developing fuel for the bomb. Back at Los Alamos, they're trying to figure out a casing so that those reactions don't happen accidentally. I can't tell you how many times I filmed that domino scene because I would knock the dominoes over with my, that kind of thing. These things can accidentally start to react. So you want to make a casing that prevents that from happening, so you can do it when you want to do that. So that's what they were working on back at Los Alamos, among many other things.
How to keep it apart and then make the critical mass occur just when you need to detonate the bomb. Because if the critical mass occurs earlier, it's gonna blow up too early.
So by July, really, they're putting all the pieces together, and you can see the first atomic bomb was test Trinity on July 16th of 1945. They are testing this in the deserts of New Mexico and Alamogordo, New Mexico, and the test was a success. And many years later, Robert Oppenheimer said, we knew that the world, would not be the same. They realized, all this work they put in, and they realized they made something tremendously destructive. Yeah,
a lot of the scientists were a little bit uncomfortable with what they were doing. And it's interesting, a thing that's fascinating to me is that they only discovered plutonium in like 1940, and by 1945, this was a plutonium bomb. Mm-hmm. It was really fast.
Yeah, and then really, essentially, almost less than a month later, Harry Truman was calling for the bomb, and this is kind of how it worked in short. So Franklin Delano Roosevelt, our president, who you saw earlier, he died in April of 1945, making Truman the president. And
Truman didn't know about it.
Yeah, until he became president. So he had this committee to kind of brief him and help him make these decisions about this kind of weapon. And the committee kind of eventually said, I think in July, or maybe it was in June, they gave the thumbs up, they gave the go-ahead that they think we should use it. And it kind of brings up that question. I think Jonathan brings it up in the book really well, but if you make this thing, why would you not use it, right? So you had a good analogy for it.
Well, yeah, you don't make a hammer and then leave it on the shelf. I mean, you get a hammer because you're going to use it.
Right. So, essentially as this process was happening, there was really no way, of stopping it. In July of 1945, the Potsdam Conference goes on between Allied nations, and they decide to send this declaration to Japan on July 26 of 1945, asking for an unconditional Japanese surrender. That was initially met with silence, and on July 31st, Truman gives the official bomb approval by this, look at this like wrinkly letter here. It doesn't say much. It doesn't say exactly what he's doing here, but he's giving approval. And as you can see, not sooner than August 2nd. You all know this, probably you've reviewed this history a lot. On August 6th of 1945, the first atomic bomb is dropped on Hiroshima, Japan. Its nickname is Little Boy. This one is actually a uranium bomb. The other two are plutonium. And in Hiroshima, 140,000 people are killed from the blast. And we see some, again, I think you've all probably seen images of just total and complete destruction of the city. If anything, just shells of buildings still standing, but not much other than that. And 3 days later, a second atomic bomb is dropped on August 9th. Fat Man is its nickname, is dropped on Nagasaki. As we said, this one is a plutonium bomb, and total destruction there as well. You can see some images from our digital collection there on screen.
And Nagasaki wasn't the original target.
No, because of weather, I think they had to change course.
They switched to Nagasaki because the other town was covered with clouds.
Yeah, and 75,000 people were killed in Nagasaki. And what I want to play, I think, Jonathan, sorry.
August 9th, the bomb was exploded above the city, and in the towering mushroom, Japan could read its doom. This was more than a routine bombing. It was the funeral pyre of an aggressor nation. The bomb had been purposely exploded high, so that the greatest part of its radioactive material was dissipated in the stratosphere. From the air, the skeletons of the Mitsubishi plants made evident that Nagasaki's war-making power was totally destroyed. For the valley area of little more than 3 square miles, blast and fire reduced the industrial plants and surrounding buildings to blackened rubble. The Mitsubishi Steel and Arms Works extended almost a mile in length. Before the blast, these were modern buildings constructed like our own American factories. Closer examination of the ruins shows the same complete destruction that characterized the ruins of Hiroshima.
That video, of course, doesn't mention the human cost, but you can see at least the physical cost on the ground there in Nagasaki. Yeah. And really, there was no real, answer to a weapon. This is the first time weapons like this have ever been used. So Japan really had, no response other than
they didn't know what it was we dropped on them. They just knew
it was that it was serious. And it led to their eventual surrender on August 15th of 1945. Those official surrender documents were signed actually on September 2nd of 1945 aboard the USS Missouri, one of our battleships. And that really brings a close to World War II. In Europe, the war had ended a few months before, and actually the 70th anniversary of that's tomorrow. And then now with this surrender, the war is finally over. Now, of course, that's, kind of the close of World War II. That is not nearly the close of the story of atomic weapons. We still see their legacy every single day today.
A big story in Iran.
Yeah, unfortunately, though, as I said, we could take weeks to talk about this, and we don't have weeks. We just have an hour. So I want to right now turn it over to Jonathan Fetter-Vorm. He is the author and illustrator, graphic novelist of Trinity. And he's going to do a little bit of a reading for you all. I'm going to actually bring it up right now. So those of you who aren't familiar with the book, and Jonathan, I think I just enabled your mic and webcam.
Ah, yeah, right.
Let's see here. Yeah, I did.
Can you hear me now?
Just want to make sure. And so whenever you get a chance, plug in that microphone, and there you go. Looks like you're about to show up right
Thanks
there.
for having me.
It's great to meet you, sort of.
All right, let's see if we can hear you. Ooh, all right. Okay, we can hear you. Yeah, you're coming through loud and clear. Thanks so much for joining us today. We're so excited to be So we had our take with a silly.
Oh, good. This is exciting. It was nice to see the domino trick actually played out with real dominoes. It's one thing to draw it in a cartoon form,
your book, and
which you're going to see now.
Be here today, and of course, reading this for everybody.
Yeah, no, it's hard to draw that. Okay, so I'm going to read from some selections from the beginning of my graphic novel Trinity, and we're going to go over some of the stuff that you covered already in the webinar. But yeah, let's go. Okay, so we start in the desert in Alamogordo the day before the Trinity test. Clearance badges. Oh, good afternoon, Doctor. This is Oppenheimer in the car. What's your name, soldier? Private Daniels, sir. Have you ever heard of Prometheus, Private Daniels? No, sir, I don't recall that name. Well, the ancient Greeks believed that Prometheus did something terrible. He broke the law of the gods when he stole a secret from them. For his crimes, Zeus, the king of the gods, shackled Prometheus to a mountaintop, and every day the punishment was the same. Every day for the rest of eternity. It's a hell of a rap. What did he do that was so bad? He gave humans knowledge for which we weren't ready. He showed us how to make fire. In the deserts of New Mexico, on a patch of sagebrush and sand codenamed Trinity, another ancient secret was about to be revealed. Atop a 100-foot tower sat the world's first atomic bomb, a construction of metal and wire with the potential to burn as bright as a star. That is, if it would burn at all. The bomb and the secret to its otherworldly fire was conceived many years before in the cities of Europe. This is Paris, France, 1898. The chemist Marie Curie and her husband Pierre discovered the elements polonium and radium, which both emitted a mysterious energy. They called this energy radioactivity. So some elements, as we saw earlier, like uranium, are inherently unstable. They throw off energy and, in the process, transform into other elements. So if you let a brick of uranium sit for, say, 4.5 billion years, chances are that half of it will have turned into lead. This is called radioactive decay, and it's happening around us in nature. So several years after the Curies discovered this, two German scientists, this is Otto Hahn and Fritz Strassmann, derived some very strange results from a rather routine experiment. Hahn and Strassmann bombarded uranium nitrate with neutrons, and instead of producing radium, they wound up with barium. These results make no sense. They must be contaminated. Let us write to Liza. A fresh pair of eyes might help. But Liza Meitner should have been working side by side with her colleagues, but the year was 1939. Liza Meitner was Jewish, and she was forced to escape from Germany as the Nazis rose to power. Meitner wrote back that she thought the results showed that neutrons were breaking the uranium atoms into pieces, and they named this process nuclear fission. It was very exciting news. Fission is the reaction that makes all the things that we associate with nuclear energy possible. To explain fission, it helps to take a closer look at the inside of an atom. So here's my version of the drawing that we saw earlier in the PowerPoint. As you know, atoms are composed of three kinds of particles: neutrons, protons, which are positively charged, and electrons, which have a negative charge. So these particles bind together thanks to the interplay of very powerful opposing forces. The electrostatic force, the big arrows, pushes particles away from each other, and the so-called strong force pulls particles together. When these powerful forces fall out of equilibrium, the atom breaks or fissions apart, like that balloon. So when Hahn and Strassmann conducted their experiment, they launched a neutron into an atom of uranium, a metal that was made up of the heaviest and largest atoms known at the time. Because a neutron has no electrical charge, it can slip through the powerful wall of electrons that surrounds every atom. You can see here this extra neutron is absorbed into the already bloated uranium nucleus, upsetting that careful balance of forces that holds the atom together. And in a flash, the whole atom fractures. Its protons and electrons and neutrons rearrange themselves into different elements. The reaction also releases stray neutrons, which fly off on their own. But the most significant byproduct of this collision is energy, and lots of it. Just how much energy comes from a nuclear reaction? About 70 million times more energy than from a chemical reaction. So if, for example, you fissioned 1 kilogram of uranium, about the size of a ping pong ball, it would make the same size explosion as 20,000 tons of TNT. One little chunk of uranium has more potential explosive energy than a pile of TNT stacked 10 stories high. If fission could work on a large enough scale, instead of just one atom at a time, mankind stood to gain more than merely the ability to make explosions. In fact, fission promised to reveal some of the deepest mysteries of the universe. So here we're going to jump ahead a little bit. This is 1939, before the Manhattan Project has really gone into full swing. And here's Enrico Fermi and Leo Szilard. Szilard and Fermi had demonstrated a dramatic phenomenon particular to nuclear fission, a chain reaction. Achieving a chain reaction is the single most important concept in the production of nuclear energy. Okay, so remember that fission produces three things: a staggering amount of energy, new atoms, and a few stray neutrons. The energy from fission is what makes bombs and nuclear reactors so powerful, but that energy means nothing if you can't get more than a couple of atoms to fission. In other words, the only way to get any significant amount of energy is to fission as many atoms as possible, and all at once. This is where a chain reaction comes in. And here are the dominoes. The concept of a chain reaction is relatively simple. The product of one reaction is enough to start another reaction. In this model, let's say that the fission is the act of tipping over dominoes. If the dominoes are lined up too far apart, the reaction stops. But if they're lined up perfectly, close enough together, then all you have to do is topple the first domino in the row, and the rest will fall. The same is true of fission. With enough atoms arranged in just the right configuration, a reaction can go on indefinitely. We're going to skip ahead now. Now we're in the height of the Manhattan Project, and General Leslie Groves, who we've met, and Enrico Fermi. Groves had built the factories necessary to make bomb fuel, and Fermi had demonstrated the viability of making a chain reaction. Only one facet of the atomic bomb was still missing, and that was criticality. Criticality is a term used to describe the ideal conditions for a chain reaction. A row of dominoes is critical if each domino that falls knocks over one other. Fermi assembled a critical mass of uranium in the reactor, and he achieved a linear chain reaction, which is to say that each atom that fissioned caused one other atom to fission. Theoretically, this sort of reaction can go on forever if you have infinite atoms, but it's not going to get any bigger. A bomb, however, requires something more explosive, a chain reaction that grows exponentially. A bomb requires a supercritical mass. So imagine an area the size of a basketball court and a pile of dominoes. To make a supercritical mass, line up the dominoes so that each one that falls will knock over two more dominoes, and each one of those will knock over two more. I wish that we could have done this in a basketball court. This would have been a much more fun demonstration. But this is essentially what's happening inside the core of an atomic bomb. The reactive material, uranium or plutonium, is packed together so tightly that when one atom fissions, the released neutrons can't help but to hit two more atoms, causing them to fission as well. In other words, once a supercritical mass is assembled, an exponential chain reaction is practically inevitable. Variations on this kind of supercritical reaction happen often in nature. Avalanches, epidemics, but it's a lot harder for humans to recreate these sorts of complex systems. A supercritical reaction requires an astounding amount of work and organization just to get all the necessary pieces arranged in the right order. All this work, whether it's lining up dominoes or enriching uranium, builds toward one single moment. The moment when what was once impossible becomes inevitable. In that moment, the logic of the chain reaction takes over. The fire will only stop when there's nothing left to burn. So, now we're going to skip ahead further. This is the night before the Trinity test. Members of the Armed Forces Public Relations Department are busy drafting press releases. One to explain what was likely going to be a very big explosion, and another in case that explosion proved to be too big. Outside the command center, scientists were watching from spots. We're staking out spots from which to watch the blast. Sorry. This is Edward Teller here. What are you doing? They told us to lie like this to shield our eyes. Nonsense, he said. We must look the beast in the eye. Here's some other scientists. Hey, what's in that bottle? Suntan lotion. You want some? Just in case. And then Enrico Fermi. It's a simple diagnostic, really. If I drop these scraps from a fixed height and measure their drift as a function of displacement from the shockwave, and in the control center, the X unit is fully charged. 30 seconds now. T minus 15 seconds. T minus 10 seconds. T minus 5 seconds. 4, 3, 2, 1, 0. In the beginning, there was only a spark. It leapt from the firing switch across the leads of 32 detonators. The spark ignited the explosive lenses, which focused the force of their blast inwards. crushing the plutonium core into a supercritical mass. The first plutonium atoms began to fission, releasing energy and excess neutrons, which went on to fission more atoms, which fissioned more atoms in turn, and so on exponentially. As the fissioning atoms released their boundless energy, the surrounding material heated up and expanded outwards, until the remaining plutonium atoms were too far apart for the reaction to continue. But just as the quantum reaction came to an end, the visible explosion roared to life. Energized material, hotter now than the surface of the sun, blossomed outward in a churning sphere of superheated gas. The rest of the world fell away into darkness. There was only the light. In these fractions of a second, the atomic light was still pure. It was not yet a bomb. It was not yet a symbol of apocalypse. It was not yet a part of our world. In these fractions of a second, the atomic light was still as timeless and indifferent as the universe itself. The darkened eyes of observers in the command center more than 5 miles away saw a sudden flash to the east, the glow of the atmosphere burning like the filament of a light bulb. The ball of fire glared brighter than 3 suns on a clear day, so bright that 50 miles away a blind girl turned her head and asked, "What is that?" Oppenheimer, speaking years later, recalled his reaction. "We knew the world would not be the same. A few people laughed, a few people cried. Most people were silent." I remembered the line from Hindu scripture, the Bhagavad Gita. "Now I am become death, the destroyer of worlds." Robert, it worked. The gadget worked. Let me shake your hand. And this is a real quote. "Now we're all sons of bitches." By the next morning, the weather had cleared, and the only evidence of the test was the twisted stumps of the steel tower and a crust of green radioactive glass, the result of the incomprehensible heat that blasted the desert sands. What began as an experiment was now a working bomb. The Manhattan Project had transitioned over from the realm of science into that of politics, diplomacy, and war. The chain reaction had started.
All right, Jonathan, thanks
great.
so much for reading that. I was just so
That's
captivated.
That's great.
I think everybody was so captivated too that I'm waiting on some.
Well,
student
for me, a
questions
big
that come
part
in.
of it was that my grandparents actually worked on the
So
Manhattan
I have
Project.
my own questions.
They were out in the
That's
deserts
okay with
in
me.
eastern Washington at the Hanford
I want
reactor,
to know.
which
I
is
mean,
where they
can
developed
you tell us a
plutonium.
little bit more? What?
And
what
so I
got you
remember
interested
growing
in the
up hearing
topic?
stories from my grandfather. He was a welder, didn't know anything about radioactivity, but he worked on the project, and he worked on it for years without knowing what he was building because it was all so secret. And they didn't. The first time they realized what they had done was the day after the bombs were dropped, and they read it in the newspaper. So I grew up hearing this story, which just seemed too crazy to be true. And so I started researching it, and I actually included my grandparents in a couple scenes here. Yeah.
Did you? Oh, that's. I'm gonna look for
That's
them
great.
now in the book. See if I can.
Well,
see if we
one of the
can
great
spot where
things
they
about the
are.
Manhattan
That's
Project
so
was
awesome.
that the government
Can you
kept
tell us? I mean,
incredibly
what
good
kind of research did you
documentation of
do
what they
on
were
this?
doing.
I
So they
mean,
took photographs of
compile. I
absolutely
mean,
everything, and a lot of
are
those
you drawing
photographs
from
are in
images
government
that you collect?
archives
How
that you
did that
can
exactly
research
work?
online, or you can, they're open to the public. So I had a lot of photos that I was drawing from, and then probably the most fun part was that I went around to all of these sites. So twice a year they open up the Trinity test site, and you can actually drive out in the middle of the desert in New Mexico, and you can walk around at ground zero. And those twisted stumps from this last scene, they're still there. There's still these concrete stumps, and that's all that's left after the blast. So I spent about 2 weeks driving around the West, going to these nuclear test sites or power plants or actually nuclear disposal facilities. So that was pretty fascinating. I got to do a lot of drawing from real life there.
That's so awesome.
That's a good question. This was my first one, so I was sort of, trial and error.
So you say, I want to do a graphic
A big part of
novel,
it was
and it's like,
was starting with
process? And then
individual
research, and
scenes,
you
like
drive
some of the
around,
things
and
that I
then
just read
how
to
do you
you.
put together an entire book,
I guess coming up with the idea of Dominos, that was an important one. Trying to come up with visual metaphors that you can use to try to explain the science. And then once you have those, then I link it with stories of characters that I like. And the big thing about this story was trying to organize it in a way that both made sense for the science, helped explain the science, but then also helped it do the history, helped communicate the history of how these bombs were used. And so the book, I divided it into 3 sections, which is convenient because not only the fact that the book is called Trinity and the Trinity test site, but that there were 3 atomic bombs used. And so each one served a different purpose. The Trinity test was to talk about the science. The Hiroshima test was to talk about some of the moral implications and what the bomb did to cities. And then the Nagasaki explosion was the use of the bomb against people and to show what the human cost of it was. So that was how I structured the thing. But yeah, to make a comic, it just started out doing a bunch of little doodles, doing some sketches, writing a script, sort of like a movie script, explaining what each panel is going to do. And then lots of drawing over and over again for years. That's a good question. So the thing about comics is that there are so many different stages. You start with a script and then sketches, and then you do pencils, and then you do inks and lettering. And so you're going over the same material over and over again. So when I wrote it, it was sort of haphazard. It was a scene here, a scene there. But then I was sort of careful when I was drawing it that I would save that I started at the beginning and drew to the end. Although I would jump around once in a while, because the thing about drawing 150 pages is that you get better at drawing over the course of it. So I wanted to make sure that the first drawings weren't really bad and then the last drawings were really good. So I would switch it up a little bit. I'd sketch a page in the beginning and then sketch a page in the end so that people wouldn't necessarily be able to see that I was getting better at drawing hands, which I definitely did by the end of it.
We're getting an interesting question from this is from the McFarland family.
For sure. Yeah,
they were asking if
so
did you talk with
to get to
anyone from
the
Japan?
first question. No, I didn't talk to anyone from Japan. I wish that I had known someone that I could have talked to. Subsequently, since the book has come out and it was translated in Japanese, I have had conversations with people who are mainly historians or scholars of the time period. But one of my goals in writing this book was to try to tell parts of the story from the Japanese perspective. In terms of talking to other people involved with the project, I sent the book or versions of the script and drafts of the book to 2 scientists who actually worked on the Manhattan Project, and they both helped to check the science, make sure I had it all right, and then also they did a good job of telling me, anecdotes about what it was like working at Los Alamos or what it was like working at Hanford. And then, like I said, my grandparents, I interviewed them and wrote down some of their stories about what it was like working in a company town as workers there. And then online, again, there are a lot of diaries and a lot of journals online that have been declassified that the government, you can access, and you can learn a lot about what the experiences of people were like just from that. And it's fun too. It was exciting to get to read. It's amazing to read diary entries. I mean, because a lot of the people who were fighting in World War II were in their,
hear that out there, students,
late teens, early 20s. And at the time when I was researching this book, I was reading the journal of a guy who was on the plane that dropped the bomb on Hiroshima, and he was my age when he did it. And it was amazing to be able to, read his diary entries. Mm. Yeah, I
Take
actually
a look
used
at
that a lot
poetry on
for
our
Trinity.
blog
It was
about
really helpful to
the
understand the
called
science.
the Los
I
Alamos
also they have all the
experiment. It's like
equations, and I
physics
used those
book
equations on the
used to
blackboards and
teach
the
all the new
drawings.
scientists that came onto the project. You can download the whole
They don't
book
make any
and
sense to
read
me,
the
but
whole thing. Yep.
yeah,
Aren't they beautiful? I love those equations. And I could tell looking at your book that those diagrams they made of the model of the bomb and how it was going to go together, I could see
I was
you use that for your book.
one of the things that I sort
Is
of
there
knew
anything
about but
through your
didn't really
research or through,
appreciate
the
until I
time of
researched the story
creating
was
this whole thing
just
that
how
surprised
big
you
the
that you didn't
secret
know about
was
the
of the Manhattan
or the
Project?
bombs or anything like that?
Hundreds of thousands of people were
Came
involved, and
across it was
only
like,
a few dozen of them knew what exactly was going on. And there was even a time when the president, when Truman took office, before he even knew that an atomic bomb existed. So it was amazing that you could do something on that scale that cost so much taxpayer money and was completely secret. Yeah.
It was like a couple weeks that he.
it's unbelievable. All right, well, I see if there's any good other student
Yeah,
questions.
exactly. Yeah.
in
So this is just
here.
the first. The
Oh,
Trinity
well,
test is
actually,
essentially the first half
public
of the
library
book,
in
and then
Alaska,
the
they were
rest is about
wondering,
Hiroshima and
how the book
Nagasaki.
ends. Does it
And then
end
the
with
book
Trinity
actually
test? And we can tell
finishes
them
in
no,
modern
right?
day.
It
It finishes
keeps going
out in
on,
the deserts in
but
New
we just couldn't
Mexico
read the
at
whole thing,
a
right?
nuclear
So,
waste disposal site. Well, my next project is actually, it came out 2 days ago. It's a graphic history of the Civil War. It's called Battle Lines. And I started that while I was
So
also
I want to
working
ask, and
on the
somebody else
A-bomb
asked this
book on
too
Trinity.
online.
So
What's your next project?
it's been a long project, but it's finally out now. Yeah, exactly.
Cool. Well, now I'm going to finally learn some Civil War history.
so yeah, in addition to getting Trinity, yeah, so now there's 2 Jonathan Fetter-Vorm books out there that you all can buy. Okay, so I have a closing question because I know we're kind of getting towards the time. This is, I guess,
Well, I
for
think
all of
that
us.
the 2 things. I
You
think,
know,
first of all,
I'll throw
the
it to
threat of
Jonathan first, and
nuclear
maybe we'll take it.
attack
I mean, why do you think people
has
should
diminished
still learn
since the
about
Cold
this
War, but
subject? You know,
these
why is
bombs
this
are still out there,
still,
and there are still
I would
thousands
say,
of
what
them.
can
So the
students
more
learn
that
about this
that
and
people
take with them?
understand that nuclear weapons, how terrifying they can be, that it's an important thing to know about. And then I think also the idea of government secrecy, of trying to learn as much as we can about the history of projects that are being funded with taxpayer money that we don't necessarily get to vote about. That all started with the Manhattan Project, and it's a legacy that we're still grappling with.
Do you have anything to add to that, Rob? You know?
Yeah, I think. I mean, I'm a pro-science kind of person, but at the same time, I think that scientists need to have a responsibility for thinking about those tools, those hammers they make, and the bombs they make. You know, we just saw the news that some Chinese scientists have been editing, genes in embryos. And it's like, just because you can, should you? I think that question will always be there for us. And I think it's not just big things like that. I mean, we're still dealing not just with the nuclear effects, but I mean, a lot of health concerns today are about new materials and plastics that we make, and those were all World War II things. And so I think it was a time when we made huge strides and advances, and we solved a lot of problems. But when you solve problems, you create problems that you don't know about yet. So.
And I think didn't some of those scientists, a part of the Manhattan Project, realize that, like Robert Oppenheimer? I mean, he, you know,
he was an outcast after this because he really
it's a bizarre encounter between Oppenheimer and Truman, in which Truman, after the meeting, promises to never let that guy in the office ever again,
John, in the book, don't you show an
because Oppenheimer was so outspoken against nuclear weapons after he built one. Yeah. I do, yeah. It's my last name. It's
Yeah, and
it's www.fettervorm.com.
What did I
There's
do?
a hyphen
Yeah.
between Fetter and Vorm.
So
yeah, you
actually,
can
one more for
go
closing.
online. You can find me on
Mariana
Twitter,
is wondering,
Facebook,
do you have
and
a
a lot of
website?
my art,
And
especially for
do
my
you share
new
it with
book,
them? I
which
know
just
you
came
do,
out.
so
It's
tell
all
them
all
how
online.
to get.
So
All right.
yeah.
Awesome. Well, unfortunately, we're 1 o'clock my time, 2 o'clock your time. This has been such a wonderful conversation that, as I said, I kind of feel like I want this webinar to go
do.
on,
Thanks
but
for having me. This
I
has
want
been
to
fantastic.
respect also teachers' time too, because I know they don't have endless hours in the classroom to talk about this. So, on that note, I want to say, Jonathan, thank you so much for participating in this, and Rob, thank you as
Yeah.
well.
And you can. If
I just
you
want to
have-
thank you guys. This has been fantastic. This is
If you
exciting.
have an Ask the Expert thing at the museum, you can email questions, and you can find out a lot of stuff on our website.
Yeah. So, Jonathan, I think we cut you off. What do you want to say? Well, and everybody out there watching, yeah, thank you so much for tuning into. I learned a lot, and I've enjoyed hanging out with these two guys. I hope you did too. And I think to close out for today, I'm gonna switch it over to one more area. We're gonna go away, but you're gonna see some of the things that Rob was talking about. This is our Science and Technology in World War II website here at the museum. And you can actually go there right now, and you can ask an expert question there. And also here you can see, this is our last webinar for the school year, which I'm kind of sad about. But we'll have more next year, which is great.
Year. And if you miss us, you can watch this one over again.
Yeah, so we'll have the recording available. I will send it to information about that to all of the teachers. It'll eventually be archived on our website. And then lastly, you saw, of course, you can buy Trinity if you enjoyed that reading so much as I did, and you would be interested in purchasing it. I mean, you can get it anywhere, but of course we have it at our museum store for a little bit of an extra discount.